Good morning, folks. We're going to move a little bit further ahead with how to find these limits of functions. If you haven't figured out already, uh, using a table of values to evaluate a limit or trying to graph it and then understand behaviors of the graph might be, well, obnoxious. Certainly time consuming, definitely tedious, not always the most efficient way to navigate a limit. So let's tackle these. Not to mention some of the graphs, you might not even know what the graph looks like for some of these functions. Right out the gates, the first equation, I don't know what the graph of this looks like, and I don't need to know what the graph of this looks like in order to evaluate a limit. So what we're going to do today is all of the algebraic tricks associated with finding these things. So your first strategy right out the gates is going to be direct substitution. When in doubt, plug the value the limit is approaching into the function itself, the expression that you're taking the limit of. It doesn't always work. And even when you can plug the value in, we've already seen numerous times where the function's value and the limit value don't agree. So two words of caution with direct substitution. One, you're not always going to be able to plug it in. Two, if it is a piecewise function, one that the expression changes based on the value of x, I would not necessarily recommend this approach. I would maybe try to use a table of values instead because there are some tricky behaviors to piecewise functions. Now, that being said, this isn't a piecewise function. It does have domain restrictions, but not at 3. So we can go ahead and plug 3 into this, and we get a limit value of 1/4. Now, if you do a table of values or you use Desmos or a graphing calculator, this would also agree with that value of 1/4. Excuse me. So let's see some limits where direct substitution does not work. So it doesn't mean just because I plug in 0 and I get an undefined value here, that doesn't mean we don't have a limit. It just means I don't have 0 in the domain of this function. We've seen a lot of functions already, the graph of which has a hole at a particular x value, but the limit still exists at that x value. So being undefined doesn't mean much in terms of limits. So when you have an expression that has a square root and some other term in the expression, that we've seen before simplifying, and you've done something called rationalizing the denominator. And we do that by multiplying by the conjugate of your expression, okay? So this is going to be rationalizing the numerator. Now, that requires us to multiply the numerator and denominator by this conjugate expression. Keep in mind, the expression that we result in here, which I believe is this, okay? Keep in mind the difference of squares when I have one minus an expression, one plus an expression. It's your first item squared minus the second item squared. So that square root's going to end up canceling. And if you don't see that and you FOIL through, you're still going to get this expression. Now, keep in mind, this function is not the same as the original function. It's going to end up having a different domain. But, and this is a very important but, this function that has a different domain has the same limit behavior for all x values as the original one does. And because we're dealing with limits, that's what's important here. So at this point, we're going to simplify the numerator just a little bit more. You see that I distribute the negative and the ones cancel out. And then, of course, the x in the numerator and this factor of x in the denominator also are going to cancel out. And that leaves me with just the -1 and my conjugate in the denominator. Well, that's an expression that when I plug 0 in will now be defined. So plugging 0 into the new expression results in this value -1/2. And that ends up being the limit of the original expression at 0. Now, one more time, though, keep in mind the original has a domain restriction at 0, but multiplying by a conjugate and simplifying, we no longer have that domain restriction. Different functions, but they will have the same limits. And that's very useful with a lot of these algebraic strategies. Let's move on. So part C, different type of strategy. This one's a little bit easier and a little bit more familiar to students. We have a rational expression here. So obviously, if I plug in -4 into this rational expression, I'm going to get a quickly undefined value. And in fact, what ends up happening is you get 0 divided by 0, which is still undefined, but 0 over 0 is like a nice red flag that says there's definitely something we can do to simplify. If I got something like 5 over 0, that would probably mean something like no limit, does not exist, or possibly an infinity limit. But 0 over 0 is a nice signal that I can do something more. And you probably already guessed it. I can factor the numerator and I can hopefully get something that matches with x plus 4 and reduce. And of course, that's exactly what happens. The x plus 4's reduce. Now keep in mind, again, this is a case where the new expression and the original expression are not the same. They have different domains, but they have the same limit. The new expression is something I can plug -4 into because it doesn't have a domain restriction at -4. So plugging in the -4 and evaluating, I get my limit value. Now this -13 is the value of the limit here. It's also the value of the limit of the original, okay? Now, before we move on to our last example, I do want to note something. All three examples, and you're going to see it again in part D, notice I've been carefully bringing down this limit notation step to step to step. That is not only important, that is required, all right? It's the limits of these expressions that are the same. It's not the expression themselves. So if you drop the limit notation and you only have 3x minus 1 equals the limit of this expression, that's going to be marked wrong 100% of the time. I am going to enforce that pretty strictly when I ask for work submitted. And I can promise you next year, all of the calculus teachers are going to mark that wrong. You're going to lose points for not bringing down the limit notation. So consider this your first warning, and I'm going to repeat myself probably every video we deal with limits from this point on. This limit notation, you have to carry this down step to step to step until you're ready to do the direct substitution, okay? Without that, you're calling two things that are equal actually not equal, okay? Now, let's go on to our last example today. We have a pretty crazy looking rational expression and complex fraction. So if I plug 0 in, I end up getting 1/4 minus 1/4 all over 0. So it's undefined, but it's that 0 over 0 representation again, which is a good thing. 0 over 0 typically means it's going to simplify further some way, somehow. So in this case, we have a complex fraction. So we've seen these earlier in our math journey, okay? So this is something where you can combine terms in the numerator to make the numerator a single fraction. So we're going to look for a common denominator in the numerator. And once we have a single fraction divided by this term, you simply multiply by the reciprocal. You're basically eliminating one level of a fraction. So your numerator, when I combine using a common denominator, I end up getting this. I skipped a little bit of work, but I trust you guys can figure this out. Hit pause if you need to. I'm going to quickly join a few of the common terms in the overall numerator, this level right here, and I end up with this. Negative x over 4x plus 16. That fraction is my numerator. The denominator, the overall denominator, is just x. So I'm going to take my overall fraction in the numerator and I'm going to multiply it by the denominator's reciprocal, 1 over x. And then very nicely, a couple chain reactions fall into place. When I multiply by that reciprocal 1 over x, the x's here in the first numerator and denominator at the second cancel, and that leaves me with an expression that is no longer undefined at 0. Again, different function, same limit value. So at this point, I can finally direct substitute in my 0, simplify, and I have a negative 1/16. So I'm going to post a worksheet with, I think, 12, maybe more, algebraic limits. They're all able to be justified algebraically. I'll say it that way. But in tomorrow's video, I'm going to go over one of the more challenging examples from that worksheet, but I want to give you a little preview of a variety of it. I'm not going to give you the answer to this. I'm going to kind of leave you hanging at least until tomorrow's video. Find me the limit of this expression. Now, you can find it algebraically. You can also find it graphically, but I don't want you to do graphical methods, and I don't want you to do a table of value methods. They will lead to an answer, but I want you to justify it algebraically, and that's the challenge. How can I manipulate this expression using algebraic methods? Okay, good luck with this. Of course, reach out with any questions you might have, and have a good day.